Good afternoon, colleagues. It's really a great pleasure and honor to be here to have this opportunity to present our recent study on this pattern informations of coupled PDEs with transparent boundary conditions and applications. So let me start with a few, actually two simple examples to illustrate what's the main studies we are having here. Now let's start with this. Let's say we get this coupled PDE system. This is we get a two stationary Schrödinger equation. It's minus Laplace u plus this qu equal to 0 in this domain omega, and this minus Laplace v plus this q tilde v equal to 0 in this domain omega again. And obviously, there are no coupling. So it's just the two separate Schrödinger, stationary Schrödinger equations. And this q and this q tilde are two coefficients. But at this moment, you can simply take this q and q tilde to be these two different constants. Okay? And the coupling actually occurs at the boundary. So on the boundary, we have this the Cauchy data of this u and v. They are identically the same. All right. So obviously, from this simple formulation, we can easily say that u, v are identically 0. That's a trivial solution. So definitely, we are mainly concerned with the non-trivial solutions. So let's suppose there exist the non-trivial solutions to this coupled PDE, and we are, interested in finding the intrinsic structures of this u and v, and also their quantitative relation to the coefficient configuration. Let's say q and q tilde, and also the geometry and the topology of this domain omega. So that's what we call this pattern information. So we're gonna let's say now what we can have. All right. So the first one again, let me give a very simple illustration again. Let's say the domain omega got a corner. Okay. So you see this is here. This XC is the corner point, is the vertex. Now we're gonna the two linear varieties. They form this part of this boundary of this omega. And in this locally, let's suppose this coupled PD is defined here. What we can derive for sure is that there must hold that the difference of the lower order terms, I mean qu minus this q tilde v, they must vanish at this corner point. And based on this, we know that again using this uxc equal to vxc, we can further deduce that the difference of these two coefficients q minus q tilde and this xc times this uxc equal to 0. So that means either these two coefficients q and q tilde, they vanish, the difference vanish at this corner, or this solution u and v, they must vanish at this corner point. So we prove this. All right. So this is what we call a local pattern. It must vanish near the corners. All right. So now let's consider a global pattern. Let's suppose for the global pattern, now we need to consider the waves. That means we need to consider this coupled spectral system. This is again this two stationary two Schrödinger operator is minus Laplace u plus qu equal to lambda u, and minus Laplace v plus q tilde v equal to lambda v. Here, this lambda is a real number, signify this eigenvalues, and also again we get this coupling on the boundary. All right. So now again we see that this u and v identically 0 is a pair of trivial solutions. But does there exist non-trivial solutions? Indeed, there exist many. So this spectral system possesses the same spectral properties of this Dirichlet Laplacian. For example, there are many real eigenvalues, lambda 1, lambda 2, and 2 to this lambda n goes to infinity. And for all those eigenfunctions, if you plot them out, you find that many eigenmodes exhibit this boundary localization behavior. That means their L2 energy localize near the boundary of the domain. Here I give some simple illustration. All right. So you see that when this arguments they goes inside this domain, interior of the domain, they decay very rapidly. So that means the energy basically localized on near the boundary. Okay, so this is what we call this a global pattern. So why we call it global pattern? Because this type of boundary localization behavior depends on this, the fact that this problem is defining the whole domain. And also coupling of the boundary condition is given, it's prescribed on the whole boundary, right? So this is the two simple illustrations. All right, so now I can give this general, setup of our study. First we got this, P1 and P2 are two partial differential operators. We got this P1 U equal to 0 is domain omega, and the P2V equal to 0 is the domain omega. And on the boundary, we got this two boundary operators, B1 and B2, and they specify the relation between this U and the V, and also this gamma is part of the boundary. So if this gamma is the whole boundary, we call this is a global problem. If gamma is just part of this boundary, this is called a local problem. All right. So here I give several remarks. First, P1 and P2 could be linear or nonlinear. It could be time dependent or time independent. It could even be of different physical origins. Okay, not necessarily they have the same type. Of this Schrodinger operator. Okay. The second remark is omega may be bounded or unbounded. It may be space-time domain for time-dependent problem. Remark 3 is in general we require this is BGA. They form this boundary operator. They form the normal system of this boundary conditions for this operator BGA. So that means actually this type of a boundary condition specify a certain of unique continuation principle such that the solution can be extended beyond this boundary. So this is why we call this is transparent boundary conditions, right? So the theory is that for this the previous general formulation, the coupling only occurs at the boundary, but actually in our study, it not necessarily only occurs at the boundary, but it actually occurs within the PDE. That means we got this P1 and the P2. They both depend on this U and the V, act on this U and the V. So we got this type of very general formulation of this so-called coupled PDEs with transparent boundary conditions. And we want to find the intrinsic structures of this U of the solutions, U and V, and with respect to the coefficient configurations of this P1 and P2, as well as the geometry or topology of this domain omega. So that's this the main aim of our study. All right. So now the natural question is why we consider this type of coupled PDEs with transparent boundary condition. So it turns out this type of problems occurs in a variety of applications associated to different scenarios, physical context. Okay. Now let's consider let me give some give some discussion about that. Why we study this type of PDE. All right. So the first one is the so-called inverse boundary problems. I'm working on inverse problems for partial differential equations. So the first one is naturally arise in this inverse boundary problems, also known as this Calderon's problem. So this is a classical inverse problem in this a series of inverse problems. Okay. Let me give again. Let's start with this simple example. And to illustrate this idea, and also I show you why we can have this coupled PDE that I discussed before. All right. Now let's consider this boundary value problem. We get this minus Laplace U plus this Q U equal to 0. In domain omega, let's say it's the bounded domain. And also we specify that the boundary condition is the Dirichlet boundary condition. We get this U at the boundary omega is phi. Okay. So this is let's say this is 0 is not this spectral of this Schrodinger operator, and we get a well-defined system. In particular, we got this so-called boundary operator, the Dirichlet map, is given by it's lambda q. It's maps its declared data to the Neumann data of the solution. All right. So we got this so-called boundary operator. Now it's the inverse boundary problem to recover the Q by knowledge of this lambda Q. So in the practical scenario, it's kind of like the potential field, the boundary information of this potential field U, and you want to recover this coefficient Q. So that's this Calderon's inverse boundary problem. So now, okay, now the question is this. The first question is this: is the unique identifiability whether we can really recover this Q by knowledge of this lambda Q by using the boundary information of this potential field. So that gives this, the unique identifiability issue asks, is the correspondence between this lambda Q and this Q one-to-one. So that means, if you get a Q and a Q tilde, can we conclude that lambda Q equal to lambda Q tilde if and only if this Q equal to Q tilde? All right. So from from this direction, the Q equal to Q tilde, we can immediately infer this lambda Q equal to lambda Q tilde. It's the forward program. It's well defined. But the most challenging part is that if we know this lambda Q equal to lambda Q tilde, can we conclude that this Q equal to Q tilde? All right. So now let's prove this. We use the standard a contradiction argument. Okay. Let's see what happens if this unique identifiability does not hold. Right. So in that case, that means there exists Q different from Q tilde, such that this lambda Q phi equal to lambda Q tilde phi for some phi, right? So immediately we got this, for this associated with the Q, we got this potential field U. It's minus U, Laplace U plus Q U equal to 0, and the minus Laplace V plus Q tilde V equal to 0. And on the boundary, we get this U equal to V because we got the same, same input, right? That's the declared data. And also they generate the same output is this Neumann data. So we got this Poisson U equal to Poisson U V. All right. So that means if this unique identifiability does not hold for this Calderon's inverse boundary problem, we immediately get this coupled PDE with this transparent boundary condition. Okay. Now, so the classical result due to this Alp Calderon and this John Gunther Ullmann and John Sylvester, and from this University of Washington. Okay. And they state that if this coupled PDE system holds for any phi, for any phi, that means if this coupled PDE holds for infinitely many solutions, for any possible solutions, that means you specify any input, U and V could be arbitrary, and you always get this output. They're the same. So if this is true, so this classical result states that this Q must be identically the same as Q tilde. Okay? But here now, that means what? If you're using, that means we must use infinitely many measurements. Namely, we have to use this type of boundary information, phi, lambda Q phi, for any phi on this boundary omega, and we can uniquely identify that Q. All right? But now the natural question is, the use of this lambda Q, namely infinite many measurement, is only a sufficient condition for this unique identifiability. Is it necessary? Can we reduce the use of this measurement data? Let's say only why is this coupled PDE system only holds for only one pair of U and V, only one pair of U and V. Can we conclude that Q must be equal Q tilde? Okay, this is one natural question. Okay, another natural question is, what if this partial boundary measurement, namely only this this coupled boundary condition only hold on part of this boundary, that corresponds to the use of the partial measurement. Okay, can we still conclude that Q equal to Q tilde? Okay, so this is all these two questions, they are long-standing problems in this field of the inverse problems. So now, all both questions lead to the study of this capital PDE with this transparent boundary condition. And now, as we call that, we already proved that if this domain got a corner, and on the at the corner we prove this q minus q tilde xc times this uxc equal to 0. So that means immediately implies that if the uxc, the input, the declared input of this u is not 0, then no values at this corner, then we must have this q and q tilde, they must be the same at this xc, right? So that means what? That means if this domain is a linear variety, and then if this uxc is not 0, if your input is not 0 here, we can determine that potential q, the up to the 0th order approximation. Okay, so now based on this, we can immediately do this, iterative manner. We can do this algebraization, procedure. That means if we replace this, this boundary by this, high order varieties, and this gives us this semi-algebraic domain, and we input a measurement, for example, not necessarily one measurement, but a measurement. That a measurement, that's u, the declared data, it's the derivative that not vanishes up to this nth order. So then, if this q, we can determine that the q locally around this boundary point up to this a minus 1th order. That means all the Taylor series expansion, we can determine up to this nth order. Okay, so that's that gives us even for this simple setup, that gives us why this classical result has to make use of infinite many measurement. Because at the very beginning you're giving q is a function belong to this L2, for example. So how this infinite measurement gives you this unique recovery result is actually you use this polynomial approximation. You gradually determine that q. So actually in practice, people just make use of finite many measurement. That's enough. Because why? You always use this polynomial approximation. Okay, so even for this, you can say from this simple example, you can say studying that capital PDE with this transparent boundary condition is very crucial to deriving this result. All right. So the second motivation is coming from this quantitatively understanding this invisibility transparency phenomena in the scattering theory. And also this can provide the fundamental origin of this invisibility cloaking technology. So now let me again discuss this based on very simple classical model. All right. So we got this omega. This gamma is a scattering. It's an inhomogeneity. Let's say you can take this as an aircraft in this in this space. All right. So this gamma is its refractive index. This omega is the support. Let's say take it as an airplane. Okay. So now how to induce this scattering? So we send a wave. This UI. We send a wave. This UI is a Fourier mode. It's a simple Fourier mode. It's actually fulfill this Helmholtz equation. Laplace UI plus its k squared UI equal to 0. Its k is the frequency. Right. So now this is the Fourier mode. It's take it as sine, cosine, okay, whatever. Okay, that's the simple Fourier mode. It satisfies this homogeneous Helmholtz equation in the whole space. Right. So now when this the propagation of this incident wave gonna be interrupted due to the presence of this space inhomogeneity. Right, and lead to this lead to this so-called perturbed wave. That's also called this scattered wave. So basically, we got this US is this scattered wave, the perturbation of this due to this inhomogeneity. Okay, and now we consider this linear wave. We got this U is this linear superposition of the incident wave, and this is scattered wave. That's the total wave. A total wave actually satisfies this perturbed Helmholtz system. So we get a 0th order perturbation here, gamma square here, right? So we got two differential PDEs. One is this instant wave. The other is that, after passing through this scatter, we get this total wave. All right. So now let's write this PDE as this, a potential here. We're gonna use all the perturbation here. That's V is compactly supported inside this omega. So we're gonna two PDEs. One is the instant wave. The other one characterizes this, after the passing through this scatter, we get this perturbation, perturbed wave field. We satisfy these two PDEs. Now the inverse problem that most people consider is to use the information of this solution, in this homogeneous space to recover this omega and gamma. So that's correspond to this practical technology like this radar or this sonar. Okay, but now what we consider, what we are considering here is that what if invisibility occurs? That is, you send a wave, no perturbation occurs. But what you observe out, a wave outside is still this wave. So no perturbation. It's just like this object is invisible with respect to your probing. Okay. So in that case, what we can have is again, that means the perturbed wave field, the scattered wave field is zero outside this omega. Outside this omega. So that means the scattering pattern is trapped inside this omega, inside this object. So that means now if that occurs, you can immediately deduce that if you restrict this instant wave inside this omega and this total wave inside this omega, they exactly satisfy this coupled PDE. This transparent bounding condition comes from this classical transmission condition for this second order PDE. So again, this is called, in the literature, this is called transmission eigenvalue problem. So whether there exists, that means what? That means if invisibility or transparency occurs, the scattering patterns are trapped inside the scatter. Those trapped modes are called transmission eigenfunctions. And it can also be shown that transmission eigenfunctions generate non-scattering waves. All right. So this actually here I want to put a historical remark is that the transmission eigenvalue problem was introduced and studied in 1980s, but in a different context. All right. But here now I want to say that there are actually the transmission eigenvalues, there are infinite many. They form a discrete set. All right. So now. But in addition to this, scattering theory that I described, for this, in the time harmonic setting, but the scattering theory also appears in studying this long-time asymptotics of time-dependent wave. Let's say you get this scattering from this Hamiltoning. This is given by the Schrödinger operator. So again, for this type of scattering theory, in this, if you under very mild condition, let's say you all get this local energy decay, so you can do this Fourier transform, reduce that into this time harmonic, frequency domain. Again, you get this scattering pattern. It's given by this, the same, this scattering operator is given. It can be reduced by studying the same scattering system here. So that means you can still study this so-called, for some frequencies, there is the transparency of, invisibility phenomena occurs. Okay, so now what are we, I'm not interested in finding whether there exists such this frequency. There exist many. I'm interested in studying whether this U and V, what kinds of pattern they must develop within this scatter. And also their relationship to the geometry of the or topology of the domain omega. Okay. Now again, let me give some sample. Give you some sample, idea on why they are practically interesting. So let's first recall this local pattern. I saw that before that this the eigenfunctions U and V must vanish locally near a corner. So that means what? That means if, let's say, you send a wave, that wave does not vanish at the corner. Actually, it does not vanish at a corner. A free mode does not vanish everywhere. So does not vanish anywhere. That means that type of wave, there must exist some free mode does not vanish at this corner. This must generate a very strong scattering at this corner point. So that means immediate application of practical interest is that, for example, let's say if you want to do this radar detection, which part of this aircraft generates the most significant scattering is this. Because this is the corner. All right. Indeed, we can prove, not necessarily at this corner. As long as this curvature, extrinsic curvature, mean curvature of this part is sufficiently large, then that scattering must be very significant. And we can actually derive this low Earth scattering energy bond with respect to this mean curvature. So that means not only this part generates a significant scattering, but also this. Even this is flat. I will show later. The wings, they're flat. But in a certain sense, their extrinsic curvature is very high. So that means this part, this part, this part, this part, they generate the most significant scattering to make it more easily detected. All right. So this is, consistent with our physical intuition. All right. So now the second is that a global pattern. Let's say we're gonna this boundary localization behavior. This boundary localization, many arguments exhibit this boundary localization behavior. All right. So this is also consistent with our physical intuition. That is, we know that this corresponds, this wave generates this no scattering, invisibility. So in order to achieve that type of effect, the wave choose a very smart way to propagate. It's actually when they meet this scatter, they slide over they propagate, around the boundary, slide over the boundary to return to its original path at the other side. Like this water flows, pass through the surface of a stone, right? It generates, no perturbation at this lower observation point. So that's why we're gonna do this boundary localization behavior. All right. Here, based on this, I wanna give the fundamental origin of the invisibility clocking. Actually, this invisibility clocking technology is sensational breakthrough in 2006. So actually, the clocking technology is gonna function as follows. So this is the target object, like this is aircraft. So you do this, a thin layer of coating. That's called this clocking material. It's a metal material, an artificially engineered material, such that it can control the wave propagation. So this is the free mode, the plane wave. When they propagate inside this coated layer, it slides over this, the surface of this target object, return to its original path. So that means that if you make the observation outside, you do not see anything here, right? So now you can see from here. So our perspective here is that the invisibility clocking is artificial in the sense that it is achieved by employing artificially engineered material devices, namely the properly designed metal material coating. But actually, this type of invisibility phenomena already exists in nature. I proved this. So the metal material invisibility is an artificially controlled reproduction of this natural invisibility. It's the same principle. So actually, philosophically, here I wanna put a remark is that we didn't invent it. We just it's already exists in nature, and instead we just discover it, understand it, learn from it, and reproduce it. Right? So this is at least our theoretical study gives some meaningful hints here. All right. So now, due to the time, I say there are many other motivations. I would skip this because I'm not sure whether I get enough time. So okay, now let's say we want to give a systematic study on pattern informations of this coupled PDE system with transparent boundary conditions like this. Okay, it's at least at this moment, I hope that I've convinced you that this is really a meaningful topic to study. And also, I do not care whether they exist. They always exist. Okay, it's derived from a different, a different, in the process of the study of other problems. We can always guarantee the existence or even the regularity. We gotta everything is good. We just want to study there, whether there are some intrinsic structures. All right. So now this is the first one is the local patterns. We call this is the vanishing induced by the coefficient singularities and the curvatures. All right. So now I'll give a very simple example here. Again, let's start with this simple example. So we're gonna this the coupled PDE. Laplace u plus is k squared 1 plus v equal to 0. This is Laplace v plus k squared v equal to 0. In this in this corner. Let's start with this corner. And we got this transparent boundary condition u equal to v, partial u equal to partial u v on these two linear varieties. All right. So now we, according to our earlier study, we proved that the difference of lower order term is actually the difference is Vxc. Because we know Uxc equal to Vxc, right? So actually we got this Vxc times this small Vxc equal to 0. We proved this, right? So how to prove this? Let me give this, I only show how to prove this, only for this simple example. But this already contains the essential idea of our study. Now, the idea is that we take the difference of the two PDEs, and then we multiply by a test function. The test function is u0 is again a solution to the PDE, and then we do this integration by parts. So after integration by parts, we know there are only two terms left. One is the volume integral, the other is the boundary integral. For the volume integral, we know that this is just the difference of this lower order terms here. Okay. For the boundary integrals, we know that it's the boundary composed of three parts. This is the two flat part and also this curved part. But all this the flat part, we know that this u minus v is the cosinus of the u minus v is 0. So only this, the boundary integral on this curved part left. So we actually get this u0 times this, u minus partial u minus v, and also this u minus v times this partial u0. So we get this volume integral connected to this boundary integral. This boundary integral only here, this part. So now we do this. Let's see, in the limit case, we want to construct a u0 such that its energy is completely localized at this xc. Let's say it's a delta function. Delta xc, for example. Let's see whether we can construct a u0. It behaves like a delta function. If it's a delta function, we know this volume integral immediately gives us this. But this boundary integral is simply 0. Because this u0 is the delta function, it's away from this xc is 0. Okay, so we immediately get this result. But now, the next thing is that whether we can construct this type of a test function such that its energy localized at this point. Indeed, we can construct this, we can do this WKB construction. We do this, we find this so-called complex geometric optic solution. This is the free mode. Its rho is a complex vector such that it times this x minus xc generate, this complex vector can generate, a negative exponent. So that's why its decay is exponentially away from this corner point. So it's quantitatively behaves exactly like a delta function. So that's why we can define this. So this is we can do this macro-local analysis, within this fifth space. So after that we can derive this. So now you can see, based on this simple example, we can immediately see that whether this corner is necessary. No, as long as this domain is curved enough to generate a complex vector to have that kind of behavior. That's enough. All right. So that's exactly means we can have this Vxc times this small Vxc is the order k to the minus alpha. This k is the mean curvature of that point, and this alpha is the regularity parameter. The more regular of this PDE solutions, you can have faster decay. All right, so we got this. All right, this is I want to emphasize this K is the mean curvature at that point. This alpha is the regularity parameter. So this corner is just correspond to the case that mean curvature goes to infinity. All right. So now let's do even more. Okay, more setup with this curvature set setting. We just blow up this. We blow up. Let's say we got a domain. We got a high curvature point. Now let's blow up this point. We blow up this point. We can form this a thin or narrow ends. So that the opening size of this end is actually related to this to the curvature, to the mean curvature at this point. Actually, in the three-dimensional case, I give two simple illustrations. In the three-dimensional case, we got a sleeve nozzle, or this is the same slab. Actually, that size, that's the opening size, is actually related to the mean curvature in this form, k to the minus 1. Okay, so in this way, we can actually, this is only three-dimensional illustration, we can actually have this, high-dimensional setup is that we get a general geometric, setup in the product space. That omega is split into two parts. It's omega s is a small space. It's omega r is the regular part, the regular dimension. So actually, in this small part, we got this small parameter epsilon. It's related to this mean curvature of this opening point here. Just think about, that's why I said before that the wings of this aircraft, they possess very high extrinsic curvature. Exactly because of this. If you view every point inside here, if you view from this regular dimension, they possess very high extrinsic curvature. All right. So from this, we can immediately derive this. The same idea is that we got this minus u is is the semi-linear PDE. It's minus Laplace v. We got this semi-linear PDE. Okay, f and f tilde. But actually, it defined in this product space. This is omega s times this omega r. Let's say simply take this as a cylinder, and with a very thin opening size. Okay, its the cross section is very small. Okay, because in that case, we got this f minus f. If we got this transparent boundary condition on this regular on this part, on this part locally on this surface of this cylinder. So we can immediately derive that f minus f tilde, the difference of this lower order term is related to this epsilon to this alpha. Again, this epsilon is the geometric parameter, is the mean curvature. And this alpha is the regularity parameter. So now, if this is true, now we can have a immediate application, direct application is that. Let's consider this the inverse boundary problem. Again, this is Calderon problem associated with this semi-linear PDE. We get this minus Laplace g u equal to this f x u gradient u is the domain omega. But on this boundary, we get this phi. But let's suppose we want to determine this nonlinear potential f by the boundary measurement. Again, the same as before. But now let's consider this domain is of this product type. And then we suppose this cross section is small. The cross section is small means its mean curvature is very high. And also we mix this measurement locally around this point, around this surface of this cylinder. Now we can say is that this f can be approximately determined by locally here by using this measurement data, right? So it's just an extension of our earlier study. So now actually, based on this, I only give very simple illustration. But actually, in our study, we can make the extension to the more sophisticated mathematical and physical setup. Actually, we can determine this nonlinear balance laws in product space by a single boundary observation. We get this general form of this nonlinear balance laws. But actually, we need this viscosity term. But actually, without this, it gives us the hyperbolic system. We can also do this. But now the tricky part is that how to construct this localized test functions. That's a little bit tricky because you have to localize this energy of the waves around this geodesics. But that's But actually, we can do this type of argument again to prove this type of pattern information. All right. So now here is our perspective. Actually, in the mathematical physics point of view, this omega s signifies the hidden dimension in the physical world. It's a small dimension. And this omega r represents these regular dimensions. Our study indicates that by locally measuring the physical quantities projected onto this regular dimension, if that's a physical process, generates some projected information onto this regular dimension. So if we can do this measurement and do this observation, that's sufficient for us to uncover the hidden part of the world locally. So this is our theoretical study indicates this. And also the crucial viewpoint here is that the hidden dimensions are small, that's fine, but they possess high extrinsic curvature in the view of this regular dimension. That's why I can produce this type of unique identifiability result. All right. And in addition to this, maybe most theoretical application, we can also have a more practical applications. Let's say we got this gas pipeline. Pipeline is that we can do this measurement on this boundary on the surface of this pipeline, and locally here we can recover everything inside this pipeline. But actually, the pipeline is not necessarily small. But because why? Because in the physical world, that's small or size is small, size is big. It's actually calibrated by the wavelengths. So you can choose this wavelengths to be big. So make this pipeline small. So you can do this kind of identification. So that's actually this small or big. All those physical terminologies. It's just a relative concept. Okay. And in addition to this, you can also consider some more practical applications. Exactly, we have this source attached to this, coupled boundary conditions that correspond to this PDE develop some singularities across some surface. Actually, our study actually indicates this, the solution behavior away from this singularity faces interface. One-to-one correspondence between this geometry of this gamma and also this f, this the source, and also this the solutions of this PDE system. Actually, this is also just a straightforward extension. And this into some purely PDE applications. We can also consider this so-called in geophysics. This is called the faults. That's not the faults within the Earth. You can do this observation of this, elastic field of this Earth on the surface of the Earth, and also it can do this identification of those faults inside this Earth. All right, this is local pattern. Now I spend 10 minutes to talk about this global pattern, but that's mainly for this wave operator. The linear wave operator, even though we can consider it's nonlinear harmonic generation, but as I postpone that, I consider this sample Y. The Py is, P2, there are two partial difference operators. As the Py_u is lambda u, P2v is lambda v, we got this coupling, all right? And now we prove that this, arguing for this is the simple arguing system. And we, most of these arguments, they localize on the boundary. There are two energy. Right? I proved this. But in addition to this L2 boundary localization, we can further show that this boundary localized mode exhibit resident behavior if they are treated as a surface wave. That means they're gonna operate much faster than this operating frequency k here. So that means the gradient field of this surface of those arguments, the gradient of this argument u and v. They're gonna, as this key goes to infinity, that gradient u, gradient v over this key gonna blow up. So that means the oscillator much faster. Okay. So actually, this is based on this generalized Ware's law and the quantum ergodicity. Due to time, I will not talk about the technical details. But actually, we find this boundary localization in the surface resonance. And this can be extended to the more general waves, it's electromagnetic waves, or this elastic waves, or even coupled physics waves. Even I believe that could also be true for this, for the gravitational waves. I believe so. All right. So in addition to this global, L2 boundary localization, we can further. So there must exist the LP interior localization. Because why? we know that due to this, the eigenfunctions is for my orthogonal system. So there are many eigenfunctions. There are two energy localized down the boundary. So that means there also exist many eigenmodes. They localized at the interior. That's easily form this orthogonality relation. So indeed, we prove that there exist many interior localized eigenmodes. Okay, but in the LP sense, the P must be bigger than 2. Actually, at the center point, it's, P is infinity. When the circle becomes bigger, and that P is bigger, it will reduce till to this the boundary the P becomes 2. And also, I get a physical interpretation, intuition for that. That's a little bit complicated for me to explain. All right. So now I talk a little bit about these applications. 10 minutes, okay? 5 minutes enough for me, okay? I talk about this. We discover all those type of patterns. It's boundary localization, surface resonance, and also I use this pattern to talk about the implication to invisibility clocking, right? But now in addition to this, philosophical application, I gonna talk about propose a new application based on those patterns. This is what we call a super resolution imaging method. So we know that the conventional imaging modality gonna function as follows. So you get this the schedule. Let's say this is a biological species. You use this the instant wave. You send the wave. You like this optical wave. You generate the response. You use this type of information. You want to do the imaging of this biological species, right? So this is a traditional method. But now we know that there are many waves. They generate no schedule. They will not propagate outside. It's trapped inside this biological species. All right. So actually, they satisfy a different, physical system, different from this, outside physical system. Outside the physical system is that the scattering system, but the inside, those trapped mode, they fulfill this coupled PDE system, right, with transparent boundary condition. And also, you send the wave, you generate the response, you do this observation, you do the imaging, you find this, you find this object. This is the traditional way. This is also the way that our visiting function in this way, right? But we know there are many waves they trapped inside. They will not propagate outside. So now our idea is that based on those observation data here, observed outside, and coupled with this new physical system, principle here, the top of PDE, we want to recover all those trapped modes, and we use those trapped modes to do this imaging. And why this is possible? First, those modes are boundary localized. They carries the geometric information of this domain. And second, they exhibit higher oscillation than this exterior mode. So that means they can generate higher resolution compared to this exterior observation data. So based on this, now let's do some. I want to show some simple examples. Again, let's say the true object, the true biological species is this square, is dotted square. If you do this traditional imaging modality, imaging method, what you can recover only is the red spot. You lose the resolution. You cannot see, right? It's too small. You cannot see. And here I think I used almost 30,000 wave data. 30,000 wave data, and what you can get is only this those red spot, no resolution. But among those 30,000 wave data, I found there are 4 wave data. There are 4 data. They generate this. They generate the trapped mode. They generate this trapped mode, and I recover those four trapped mode. I do this imaging. I almost get this square accurate. That means it's really break this resolution limit. Okay, it's the so-called diffraction limit. All right. So just based on this, I also talk a little bit about my perspective on this, machine learning. We know now this machine, data-driven approach, this machine learning approach, has a huge impact on our research. No matter whether we do this theoretical research, we have to talk about this machine learning. But here, just based on this, I want, from the theoretical point of view, I also want to show our theoretical study got some interesting implications to this, machine learning era. Why could we do this? We image the inverse problems as a structured learning process. So that's going to integrate the three ingredients. Data-driven approach, data-driven inference. We always use this observation data when I recover some missing information of this physical system. That's for sure. It's a traditional way. And also we do this physics informed regularization, and we incorporate this physics into this learning process. That's nowadays everybody talk about this. Okay, but now beyond that, I want to show this knowledge supervision is also a crucial ingredient. I'm not sure whether just based on this, physics, just based on these two approaches, two ingredients, data-driven, and you do this, keep doing, giving you all the data, possible data, you will not find this trapped mode. Okay, and given this the physical information, physical system outside of this object, still you cannot determine those trapped mode. That trapped mode are determined by our logical reasoning. We find a new system within this, for the trapped mode. It's called PDE. It's different from this physical system outside this object, and combined with this, new physical system with this data, we got this, we got all those, boundary localization and the surface redness phenomena, and use that we have this better resolution reconstruction, imaging reconstruction. That's why I think even in this machine learning, the data era, where our intelligence, human intelligence, can still play a certain role to do this knowledge supervision. All right, I think I'm gonna stop here, and thank you.
Okay, thanks very much. That was a great talk. Very interesting. So, any questions from the audience about the talk? So actually, I have a few. So, when you went back to the initial assumptions on the types of PDEs that this works for, you said this is it works for fully nonlinear, quasi-linear, semi-linear. But at one point you mentioned some difficulties for hyperbolic systems.
Yeah.
Could you say a bit more about the?
Yeah. That's a very that's a very critical point actually. That's a critical technical step. Have to differentiate between this hyperbolic system and this parabolic system and our elliptic system. The main reason is to you can take a simple example. We have to construct this type of test function. They're gonna localize, energy gonna localize that a certain submanifold in the space, right? So to do that, so the hyperbolic system and parabolic or elliptic system, they have some sharply different, rationales behind this construction. For example, you do if for the elliptic system or parabolic system, we can always do this localization because that system is we know that's the diffusion process. But for the hyperbolic system, that's the wave. It has this dispersive relations. That's gonna make it difficult. We have to localize that type of solution along some geodesics. It's not it cannot be an arbitrary submanifold. Oh, that's the point. Yeah.
Okay, and so if a priori the region, like this boundary region, this is prescribed already in your examples, or not, because you can have, if you have a nonlinear system and you maybe have like a mixed type nonlinear system where it can be hyperbolic in some region.
Oh, that's even more challenging. Even more challenging.
Because you will need to know prior knowledge of the solution
Yeah,
first and linearize around this.
Yes,
and
yes, yeah.
The type can change, so the resonance will also.
Yeah. The way you described it make it the problem even more challenging. Yeah, that's right. But actually, we need to make progress. We are making progress. Yeah. But thank you for suggesting this type of problem. Okay. Yeah.
Any questions? Any more questions? Yes.
Thanks a lot for this very wonderful talk. So I have a question for this super resolution imaging.
Yeah.
And because this omega domain, we don't know. So how do you find the eigenfunctions and eigenvalue?
Yes. You're right. That's I only illustrate this the idea, but that consists of several steps. The first step is to find using some indirect indicators to find the resonant frequency, and that's not easy. And indeed, that's not easy. And I find this resonant frequency. Then after finding this resonant frequency using such an indicator function, then we can do further, further searching of finding the eigenfunctions. Every step is not easy. It has very costly.
Okay.
Yeah,
Thanks.
You're right.
Thanks.
Right. Yeah.
Any other questions? All right. If not, then let's thank the speaker again.
Thank you.